Okay, so we're going to talk about light as a form of energy that travels in waves. You've previously done some notes on the spectrum of light, and light is not just visible light. We're talking about all forms of light. I know when we think of light, you think of a light bulb, you think of illuminating, but light also includes radio waves, microwaves, X-rays. Those are also light. We just can't see them with our eyes. So energy in a wave. What exactly is a wave? Okay, a wave is a disturbance where energy is transferred from one point to another, but matter is not transferred. If we're in class, I'd show you this. I will put some videos and some demos on the website as well, so I can explain this better to you. Okay, so the energy transfers, but the particles vibrate. They just do not move themselves. So the energy goes this way and the particles just vibrate up and down. A particle from here does not end up over here. And that's what's meant by that. So some things that we need to know about a wave. Okay, so when I say energy, it's the same thing as saying a wave. So let's say the wave's going to the left. You can imagine this is a slinky up and down. You'd have a rest position because if you weren't vibrating it, it would just be a straight line. If I shook a slinky up and down, okay, the maximum displacement would be called the crest or the high part. We measure that in amplitude. And also the trough. You can think of an eaves trough, what catches the rain at the edge of a roof. All right, a trough, a crest. These are both maximum displacements from the rest position, but one is up and one is down. Then we also have the wavelength. So what's important to understand about wavelength is that's one cycle. So if I went along the wave, like that, that's one cycle I repeated. Okay, so if you were on a swing is actually a perfect example of something that's repeated motion. This would be you swing up, and then you'd have to come back. Okay, so we have to come back to the rest. This is not one cycle, that's only half. We have to do this. So that's another half a cycle. One cycle. Now we don't have to measure it from here to here. We can also measure it from the top of a crest to the top of a crest. So this waveform is made up of I'm starting here. 1, 2, 3.5 actual cycles. Now you do not measure the wavelength along the wave. You measure it along the horizontal. Okay, this wave in particular is called a transverse wave. And when you take grade 11 physics, we'll talk about different types of waves. This wave, the particle vibration is perpendicular to the energy. So the energy is moving to the left, particle vibration is up and down. Those two things are perpendicular. I've already talked about this. Now, if you want, you can copy this out, or if you're in class, you would be copying it out, but you can obviously just print this out or do what you want. So here I just go over the definitions of all of these aspects or characteristics of a wave. Okay, lambda stands for wavelength. It's the Greek symbol or letter lambda. Lambda. That's exactly how you say it. It is one cycle. It's measured horizontally, okay, along the rest position or parallel to the rest position. Usually measured in meters. You can measure it in other units, but that would be the standard. Okay, and then we have amplitude. It's the maximum displacement on a wave from rest position. So you'd go from the rest all the way to the top, or from rest all the way to the maximum. Okay, you wouldn't measure it to here because that's not maximum. That's somewhere in between. Now we have frequency. Frequency you can't see in a picture, but it's how fast something's vibrating. So if I'm vibrating this marker, how often does it go up and down per cycle? So this is called frequency. It's number of cycles or wavelengths per second. And this is measured in hertz. Yes, like the car rental, but hertz is just another name for per second or 1/seconds. All right. Now, later on, when we're doing some calculations, we might want to know something about the wave, and actually the speed of a wave depends on the frequency and the wavelength. This is called the universal wave equation. We also do a whole unit on waves in grade 11 physics. Okay, so that's that page. If you want, you can pause it here and copy that out, or take a look and ask me questions. Okay, next. we want to talk about the wave model of light. Okay, this is page 404 of your textbook. You'll be taking some notes on that on your own. But what I want to do is talk about light. We cannot see light waves. We know they reflect off of things. That's how we see them. But we do not see light waves like we see water waves. So we use this ray model of light to explain what light is doing. So if you imagine this is ripples in a pond, so you drop a pebble or a droplet and you would see these rings of waves going out. Okay, so what we do is we use a ray to show the direction that the light travels in, or the waves. So here we would show the waves. So this is a ray. The rays would be going out from the center in all directions. And we use these, we'll be doing ray diagrams to show, because we're not going to show all the waves. We can't see them. What's important is we know the direction. So these waves are traveling out in a circle. These would be the rays. An array is just an arrow. Okay, so attached to your note is this paper. It uses the textbook on page 404 to 405 and 406 maybe, just to describe what are some properties of light, or words that we use like transparent, translucent, opaque. What does that mean? Shadows, and the definition of reflection and diffuse reflection. And this is a great demo that I do in class. I can't really do it here, but I would ask you what seems brighter, a mirror or the screen. And what's interesting is the screen is actually brighter. And when I mean screen, I mean the screen that we use for, for showing the videos. Because what happens is it's actually reflecting light in all directions, so it's bright everywhere, whereas a mirror is really only reflecting them all in one direction. So unless you're right in that Tinkerbell thing, when some people shine that light in your face, it actually isn't as bright. And maybe I can try and make a video of that to add. So you'll have this to fill out for homework, and you have some questions on the top, or your schoolwork. One other thing I want to do is we'll do drawing a wave, just so you get a better understanding of waves. Okay, so here's a drawing wave assignment. I will do the first one with you, and you can do the other two. Okay, so I don't know if you can read this, so I'll bring it up to the camera. So what you want to do is you want to draw a wave, okay, or a series of waves, and label the following on all of the waves. The rest position, direction of the wave motion, we're going to define that to the right, wavelength, direction of vibration, amplitude, and a crest and a trough. So I will do number one. Okay, number one says draw a neat diagram to show a transverse wave. That's the only kind of wave you know. It's going to be 3 wavelengths long. The wave has a wavelength of 6 centimeters and amplitude of 2. So I'm going to do that right here, and maybe I can zoom in so we can see that a little bit closer up. Okay. So I'll just choose a different color just so we can see what's going on. So this darker line right here, hopefully you can see that. I'm going to start right there. Now my wave length is 6 centimeters. Now each of these is 1 centimeter by 1 centimeter. So that means I need 6 of these. 1, 2, 3, 4, 5. That's going to be 1 wavelength, but I want it to be 3 wavelengths long. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, don't worry if you're not great at drawing waves. I think of this as like connecting the dots. So what I do is I pick halfway in between, because I know where it's going to be crossing, and halfway in between, half or 1/4, is going to be my crest or trough. Now it says here I have amplitude of 2 centimeters. So 1, 2. So there's my crest. 1, 2. There's my trough. And I'm going to go in the middle. Okay. And 1, 2. It's like making a connect the dots without the numbers. All right. Can you guys see that? Yep. And halfway, and half again. Halfway, half again. Okay, so now time to connect the dots. Now some people just want to do zigzags because they're not good at drawing curves, but that's fine. And it probably would be easier if you maybe turn to the page sideways. But you do you. I have to do it this way so I don't take it off the camera. Okay, so 1, 2, 3 wavelengths, 2 centimeter, 2 centimeter amplitude. So now let's go and label everything I need to label. Okay, so this is the rest position. Okay, this is going to be the wave is going to the right. I'm just going to use an arrow like that. And then it says, so I've done rest, I've done wave, let's do a wavelength. Okay, I'm going to do a wavelength from here to here, just so that I can see it. That's one wavelength. And if I did it right, it should be 6 centimeters now, or 6 of these squares. I can't measure, these aren't really quite a centimeter because I lied to you. So let's just see. So that's, if I do here, that's a half, but that's 1, 2, 3, 4, 5, and a half here, and half plus a half is 1, so that gives me 6. So there is my lambda. 1 lambda. So I did a wavelength. Direction of vibration. Direction of vibration is up and down. It's not just up, it's not just down, it's direction of vibration. Okay, and then I want to label the amplitude. So there's the amplitude. You could even say 2 centimeters. And then a crest and a trough. I'm just going to go somewhere over here. Crest, trough. Now I might be running into my wave down below. Okay, so you'll see that one has an amplitude of only 1 centimeter, so hopefully not. All right, so you can take a look at that. I've done all my labels, I've measured them all, so that should be 18 centimeters long technically, and because 3 times 6 is 18. Okay, so there's your work for today. Send me some comments, send me some questions regarding this material if you have any. Okay, thanks guys, miss you.